Hello, welcome to my video on current research. My name is Amir Shee. I am a postdoctoral research associate at the University of Vermont. I earned my PhD from the Institute of Physics, Bhubaneswar, and previously held a 3-year postdoctoral position at Northwestern University. I am a theoretical physicist and my research focuses on non-equilibrium statistical physics, active matter, soft matter, and biophysics. Active matter refers to systems of self-driven units that continuously consume energy and therefore operate far from equilibrium. From cytoskeletal networks and bacterial colonies to active colloids and engineered swarms, these systems exhibit self-organization, anomalous transport, jamming, phase separation, pattern formation, and emergent rheology that cannot be explained by normal equilibrium statistical mechanics. A central question in my research is how microscopic activity, noise, and interactions give rise to emergent collective dynamics and material properties at large scales. My goal is to develop precise theoretical framework and computational models that connect single particle dynamics to collective behavior in active and living systems, enabling tunability, adaptability, and control in active and living materials. During my PhD, I developed theory across scales, spanning exact single particle dynamics and cytoskeletal mechanics. For single active Brownian particles, I introduced a theoretical framework that maps their stochastic trajectories onto an equivalent equilibrium semi-flexible polymer and adopted Laplace space methods of polymer to compute exact dynamical movements in active systems. I then studied biofilaments in gliding motor proteins assay, showing that semi-flexible filaments undergo first order and reentrant transition between open and spiral conformations. Overall, my thesis established a consistent theme, identifying mechanisms and building predictive quantitative theory directly linked to measurable observables. Building on this foundation, my postdoctoral and current research has evolved into a unified program on how non-equilibrium driving controls transport, structure, and mechanical response. I pursue three closely connected directions. I develop analytical theories for active particles under torque, confinement, and stochastic resetting, and derive exact time-dependent movements of displacement in 2 and 3 dimensions. More broadly, this direction provides benchmark predictions and control maps how tuning, resetting, torque, and confinement reshapes localization, dynamical crossovers, and fluctuation statistics. At high density, activity and noise can create qualitatively new solid-like states. In our recent PRL, we identified an emergent noise-induced quench disorder phase in dense active solids. Also, I developed a linear response theory for active solids with noisy chiral dynamics, combining normal mode analysis and continual elasticity formulation to predict emergent mesoscale correlations and distinct spatiotemporal regimes. These results establish a route from microscopic driving to mesoscopic collective dynamics in active solids. In my current postdoctoral program concerns the mechanical response of dense active materials under shear flow. In a recent PRL paper, we showed that a small fraction of active dopants can strongly tune steady state shear rheology and shift glassy behavior, and that key rheological observables can be organized by an effective injected active energy control parameter. Currently, I am investigating how polydispersity and selective passivity reshape non-equilibrium glass transitions and order disorder phenomena in active and living materials. The goal is to identify robust structural and fluctuation-based signatures that can be measured in simulations and experiments, and to develop predictive theory that links those signatures to metamaterial design parameters. I co-authored a RMP review article on self-aligning polar active matter, which provides a unified framework for alignment-driven collective behavior in both natural and artificial systems. I also engage in interdisciplinary collaborations where theory interfaces directly with experiment. For example, in recent work on axonal transport, my theoretical modeling of cooperative motor cargo binding was used to quantitatively interpret experimental data on intracellular transport in neurons. Together, these efforts form the foundation of my independent research program, which I will discuss in the next video of my future research plan. Thank you for your attention.